Okay, then, uh, a very good morning to everyone. Here we are into wave optics and we are dealing with interference. This is lecture number 2 on interference. In the previous class, we had seen something known as superposition principle. Do you remember what was that superposition principle? If I just give you a quick recap, if I have two waves, I hope I am audible and visible to all of you.
Yes, sir.
Y1 is equal to A1 sine omega t. And if I have a second wave, Y2 is equal to A2 sine omega t plus phi. Phi is the phase difference between the two waves. Now, when these are waves moving in the same direction. And if the amplitude is very near to each other, very same, equal, and their angular frequency or frequency is same and they are traveling in the same direction, when they overlap, that overlap or superposition is known as interference. At some point you will get very bright fringe and at some point we will get dark fringe. Do we remember this? Yes or no?
Yes, sir.
When I add these two, y1 plus y2, I will get the resultant wave or resultant displacement, and the answer for that will be A sine omega t plus xi. And we also discussed what is the value of this A. This A is the resultant amplitude, and that is equal to A1 square plus A2 square plus 2 times A1, A2 cos phi, where phi is the phase angle between the two waves. We also saw the value of this tan of xi. Tan of xi is A2 sine phi upon A1 plus A2 cos phi. This is a quick recap of what we had done in the previous class. Yes or no? Do we remember this? Okay, then we also saw the formula for intensity, and I told you intensity is proportional to amplitude ka square. Yes or no? So the formula
Yes,
for
sir.
intensity becomes I will be equal to I1 plus I2 plus 2 times root over I1 into root over I2 cos phi will come out of the bracket. Do we remember this?
Yes, sir.
We also saw when both their intensities are same, I1 is equal to I2 is equal to I. We have a very nice formula, 4 times I naught cos square phi by 2. We also saw if the value of this phi is even multiples of pi, 0, 2 pi, 4 pi, and so on, then what happens? Tell me. If this phi is an even multiple of pi, what happens? We have the value of cos phi as plus 1. Do we remember this?
Yes, sir.
And this type of interference is known as constructive interference. If the value of phi is odd multiple of pi, that means it is pi, 3 pi, 5 pi, and so on. That means the value of cos phi is -1. We call it destructive interference. Yes or no? This
Yes,
was a
sir.
quick recap of what we had done in the previous class. I hope you can recollect what we had done. We had also seen that what is the relation between path difference, phase difference and time difference. Do we remember that?
Yes, sir.
Okay, what is wrong here? I'm not able to use it. Okay. What next? I'm having some trouble here. Okay. We will now move on to the first heading of today's chapter. And the first heading is this. I'll just get this thing on board. Okay.
सर
Yes, beta.
सर आप बोले थे ना सब चैप्टर्स के माइंड मैपिंग देंगे कब देगा सर
Oh, I forgot, yeah. I will try to give you by today. Today, maybe tonight when I come home, I will make those mind maps and I will send it to you. I had given you the mind maps for ray optics, na? Yes or no? I send you the mind maps
हाँ
for
सर
yes. So, you need mind maps for all the topics.
Yes, sir.
Okay, I will send that to you. Thanks for reminding me. Just what you do is just put a small message in the Telegram group. No, I forget things, so let me not forget it. Just put a message in the Telegram group that will remind me that I had to do this job. Okay, can you do that for me?
Hi, sir.
Okay, just do that so that I can recollect and I can give you. Shall I continue with the class?
Yes, sir.
Okay, coherent sources. Now, what is a coherent source? Now, remember, this coherent source is going to play a very important role in this chapter. If the phase difference, do you remember the phase difference was phi between the two
Yes,
waves,
sir.
y1 and y2? If the phase difference between the two sources remain constant, that means it does not depend on time. So we can have a very good and a sustained interference. If the phase difference changes, interference. Now, when I say the word interference, what I mean is at some points you will get bright fringe, at some point you will get dark fringe. Now, if the phase difference is constant, then you will get bright and dark fringe ka very good pattern. At some points, fixed points, you will get dark fringe. At some point, fixed point, you will get bright fringe. But if the sources are not coherent, that means the phase difference is not constant, you will not get interference. So the next condition, remember we had seen three conditions for interference to happen. Number one, both the waves must be moving in the same direction. Number two, the amplitudes must be same. And the amplitude must be same or nearly equal. Number three was frequency was same. Do we remember this?
Yes, sir.
The fourth thing in that was the phase difference must be constant. We did not mention it there, but if we did not mention it there, just write it now. The fourth condition is the phase difference must remain constant. Now, instead of saying phase difference remaining constant, we can call them as that the two sources must be
Constant.
not constant. The two sources must be coherent sources.
Coherent sources.
So interference can only happen, number one, waves traveling in the same direction. Number two, almost same or equal amplitudes. Number three, same frequency. Number four, the sources must be coherent. Do we understand this?
Yes, sir.
Four conditions. Now, if the conditions are met, the intensity will be given by this formula. We have already discussed this formula. How we can obtain coherent sources? There are two ways to obtain coherent sources. Remember, coherent sources of light. Coherent sources of light. And please note it down. Coherent sources of light should be obtained from a single source of light. For example, there is white light here in my room. If I want to create coherent source, there must be a single source, and from that single source only and only and only we can create coherent sources of light. Have you noted it down?
Yes, sir.
What have you noted down?
Coherent source and method of.
Coherent sources for light can only be made from a single source of light. Do we understand this?
Yes, sir.
Now, When we have a single source of light, so you only have one source of light. Now I want to create coherent sources from this source. So I can do it by two ways. I can divide the wavefront or I can divide the amplitude. Remember these two ways of creating coherent sources from a single source of light. What are the two ways? Number one is division of wavefront and number two is division of amplitude. You just need to remember this, and you need to remember the example of division of wavefront, which will be coming to you right now. I'll give you 2 minutes to note whatever I have discussed in the class up till now. So what will be the opposite of a coherent source? In coherent source, we had phase difference that was constant with time. In the other type of source, which is known as a non-coherent source, phase difference will depend on time. And therefore, the interference pattern will also depend on time. So fringes will keep on changing, and a sustained interference or a consistent interference will not be formed. As you can see, there are two lamps here, L1 and L2. Wherever you have two sources of light cannot produce coherent sources. They will always produce no non-coherent source. Do we understand this?
Yes, sir.
And you can see the formula when the sources are not coherent or non-coherent. The formula is I is equal to I1 plus I2. Remember this formula. This is the formula which is valid only for non-coherent sources. But if the sources are coherent, we already know the formula. I is I1 plus I2 plus 2 times root over I1 I2 multiplied by cos phi. Do we remember this?
Yes, sir.
I'll give you a minute to note down this concept of non-coherent sources. So, we have seen what are coherent sources and what are non-coherent sources. We have also seen that a coherent source can only be produced by a single source. Now, there are two ways of producing coherent sources. Two ways. One is by division of wavefront and the other one is by division of amplitude. Now, what you're going to see in the next screen, which is right now available, is experiment known as Young's double slit experiment. And if I can, you might have heard about this experiment. And if I may bring your attention to the fact that you can see there is a there is some light coming from the source, and from there you have created a small hole or small opening in a cardboard. This hole or opening is known as a slit. Do you understand the meaning of slit? Small hole, pinhole is known as a slit. And we have created one single source from here. Do we understand this, that this is a single source? Yes or no?
Yes, sir.
And then what you see here are the wavefronts of the single source. Now, in front of this, I have put another cardboard with not one but two slits. So when I have two slits, instead of one source, I have created two sources. Do we understand this?
Yes, sir.
So 2 and 3. Source number 2 and source number 3 are created from the source 1. Do we understand this?
Yes, sir.
This is created by the phenomena of diffraction. So the sources are created from a single source by the phenomena of diffraction. What is this diffraction? We will understand this phenomena of diffraction also. But right now you just need to understand that I have created two sources which are coherent from a single source. Do we understand this?
Yes, sir.
Now, looking at the diagram, I have told you that this is the wave front. Can you tell me by which process I have created these two sources? Have I created them by division of wavefront or have I created them by division of amplitude? I have created two sources from a single source. By which method have I created it? Division of wavefronts or division of amplitude? What is your answer? I have created them by
Linear wavefront, sir.
yes, beta. I have created them from the division of wavefront. See, it's very simple to see that on the left hand side we have one wavefront which is hitting, but on the right hand side from that one wavefront I have created two wavefronts. Do we understand this?
Yes, sir.
This tarika, this method of creating two sources which are coherent from a single source in YDSE is known as the division of wavefront wala tarika. Do we understand this?
Yes, sir.
So this is what it is written. According to Huygens, light has wave nature which can be experimentally proved by YDSE. S is a single source of light. From here, I have created two sources of light, S1 and S2, which are coherent by diffraction. This diffracted wave are superimposing. Do you see this superimposition? They are overlapping each other. Do you see all these points? They are overlapping each other. Now they are coherent sources. They are traveling in the same direction. They have nearly equal or same amplitudes. They have the same frequency because they are coming from the same source. Therefore, when they interfere, therefore, when they superimpose, they will create interference and you will see dark and bright fringes. Do you see here? There is a central bright fringe. Then there is first dark, first bright, second dark, second bright. Downwards also, after bright fringe we have dark, then we have bright, then we have dark, then we have bright. This phenomena is known as YD. This phenomena is known as interference and it is explained by this Young's double slit experiment, and you can do this experiment in the lab as well. Do we understand this? You will have to draw these
Yes, sir.
diagrams. You may not draw this diagram because you can just mark it here, but you will have to draw this diagram where you have two slits from a source created from a single source and we have alternate dark and bright fringes coming. I will give you 2 minutes to draw this diagram because this entire chapter of interference is all about Young's double slit experiment YDSE, which is an example of division of wavefront creating coherent sources. I'll give you 2 minutes to note it down.
Okay, sir.
Then we come to this screen, and in this screen again you see a diagram, and if you look, and I will give you a bigger look, and you need to draw that diagram first before understanding anything. So you need to have a bigger look at this diagram. And do you see from where this diagram has come, bacha? This has come from that previous diagram where we had two slits. Do we understand this?
Yes, sir.
So we have left the left hand side of that diagram when there was a single source. We have left that part. From two sources we have started, and then we have put a screen, and on this screen we are going to see interference pattern. Do we understand this? Do we understand this, that we are going to see the interference pattern on a screen? And I would ask you
Yes, sir.
to draw this diagram first and then I will explain it. Draw this diagram, mark everything. For example, this small d is the distance between the slits. This capital D is the distance from the slits to the screen. And this x is position of a point P where interference is happening. This theta is the angle between here and here. And this S2 from S2 to L, the distance S2 L is the path difference. I'll give you 5 minutes to note this down. This is the most important diagram. The entire chapter depends on this diagram. So draw it very carefully. Okay, have you drawn this diagram? Hello, bacha? Have you drawn this diagram, beta? The microphone is working. So what do we see here is one wave is coming from this slit S1 and the other wave is coming from this slit S2. Do we understand this? And they are going to interfere at a point P. The path difference between the two Path difference, how do we find out? I find out the distance from here to here. This is smaller distance. I find the distance from here to here. There are two ways which are coming. They are following different paths, and therefore there is path difference. Path difference is P into S2, PS2 minus PS1, and that is equal to S2L. Do we understand this?
Yes, sir.
For constructive interference, path difference must be n times lambda. We had seen it in terms of phi. Now we are seeing it in terms of lambda. It is n times lambda. And for bright fringes, it is 2n minus 1 times lambda by 2. To get the value of first dark fringe, put the value of n as 1. To get the value of second dark fringe, put the value of n as 2. To get the value of first bright fringe, put the value of n as 1. To get the value of central fringe, do we remember central fringe?
Yes, sir.
Put the value of n as 0. So you will get central fringe at the center, then dark, then first bright, then second dark, then second bright. Do we understand this?
Yes, sir.
And this is what you will have to draw, and what I explained just now. So to get the first dark fringe, apart from the central fringe, put the value of n as 1. To get the dark fringes, put the value of n as 1, 2, 3, and so on. Path difference is, you can write this in this formula. Remember this formula, path difference delta will be equal to x, where x is this value. Do we understand this? Into small d by capital D. For bright fringe, this must be equal to n lambda, where n starts from 1 for first dark fringe. For dark fringe, value of n again starts from 1. It is odd multiples of lambda by 2. For bright fringe, it is multiples of lambda. Do we understand this? Can you remember all this information, these 4 or 5 formulae? I'll give you time to note down these formulae. Can you note it down? Have you drawn the diagram, bacha?
Completed.
Okay. Do you see here? What do we see here? Do you see that this is the central fringe? Let me highlight it. Do you see that this is the central bright fringe? Do we understand this? You can see this point here. It is maximum, yes or no?
Sir. Yes, sir.
And this is where you have your central bright fringe. Do we understand this?
Yes, sir.
Then after this maximum, you get this minimum here. Do we understand this?
Yes, sir.
And this is the position of your first dark fringe. Do we understand this?
Yes, sir.
So basically what do we say is from here to here, from this half to this half, this is known as the width of the first dark fringe. Do we understand this? Do we understand this? From this point to this point, in the middle we have the dark fringe. This width, as you can see here, this width is known as, this is the width of the first dark fringe. Do we understand this? Similarly, this will be the width of the first bright fringe. Do we understand this? This is known as, and as you can see, all these widths are same, and this width is known as beta. This beta is known as the fringe width. Do we understand this?
Yes, sir.
From one first dark to the second dark, or from the first bright to the second bright. Do we understand this? Again, I will try to draw the diagram in a better way. See,
Puja.
do we see this? Do we see this? This region? In this region, you will have dark fringe. Do we understand this? All these black things are dark fringes. Do we understand this?
Yes, sir.
And behind these dark things, we have this bright things, this yellow, I mean, this thing that I marked with red are all bright fringes. Do we understand this?
Yes, sir.
This is the point of the central bright fringe, and this is the point of first bright fringe. Do we understand this?
Yes, sir.
So the distance between any two bright fringes or any two dark fringes is known as your fringe width. Do we understand this?
Yes, sir.
Denoted by the letter beta.
Okay, sir.
Distance between two bright or two dark fringes is known as beta, your fringe width. Therefore, the distance between the bright fringe and the dark fringe, this is the first dark fringe on the left hand side. Distance between the bright fringe and the first dark or the next dark fringe will be beta divided by 2, half of the fringe width. Do we understand this?
Yes, sir.
Have you drawn this diagram?
Okay, sir.
Please draw this diagram.
Okay,
and,
sir.
and mark these beta correctly, because if you understand this chapter is over as such. So first you draw this diagram, then we will write the definition of fringe width. I'll give you 2 minutes to do that. I hope
Okay,
everyone
sir.
is there. I can't see you. My lab, my iPad has gone kaput. The battery has gone, so I can't see you guys. So I hope you are there in the class. Yes.
Yes, sir.
Okay. 2 minutes to again draw beta here and understand the meaning of beta.
Okay, sir.
Okay, then.
Completed, sir.
Well done, beta. Then we come to this definition. I've already explained that this is your fringe width. This is the distance between any two successive means one after the other, bright or dark fringe is known as fringe width. This is the formula, and you just need to remember that the fringe with beta is d lambda by d. This is the formula that you must remember. Remember, part difference delta x. Part difference was x into small d by capital D. Do we remember this?
Yes, sir.
In beta, to find the fringe width, capital D has gone on the numerator, small d has come into the denominator, and lambda has come instead of x. So this is the way you can remember this. If you can remember any one of these, you should be able to find out the next of these. But if you make a mistake in any one of these, you will make a mistake in the second one. The distance between two consecutive dark or two consecutive bright is known as beta. Between a consecutive dark and bright, it will be beta by 2. Do we understand this? This is what you need to note down, and I'll give you 2 minutes to note it down. I hope everyone is there. Let's move ahead and see the next point. And the next point here is known as angular fringe width. Now, what do you mean by this angular fringe width? The fringe width that we saw was in terms of length. It was the distance between two consecutive bright or two consecutive dark fringes. You can see this fringe width, yes or no, beta? These are the two dark fringes, and we are trying to find out the distance between the two dark fringes. Yes or no?
आवाज क्लियर नहीं आ रही.
Let me see what's wrong with my voice. Okay,
Hello, sir. Am I audible?
just a minute, beta. You are audible. Am I audible? Am I
No, okay.
audible? Am I audible? Am I visible, beta?
Yes, sir.
Everything doing well?
Okay, sir. No.
Okay.
Okay.
Okay, you could have told me that. I could have, probably there was some problem with the internet connection. I just refreshed it. Am I visible, audible? You can see me dancing. Okay. Angular fringe width. Now you'll have to draw this diagram to understand angular fringe width. These are the two slits. Do we understand this? Here I will have my screen. Do we understand this?
Yes, sir.
And here I have the fringe width beta. This angle alpha is known as your fringe width. So angular fringe width, sorry. So this angle alpha can be written as beta, which is this divided by capital D. Do you see this?
Yes, sir.
Beta divided by capital D. Now beta is d lambda by small d. So you can write alpha as lambda by d as well. So these are the two formulas for angular fringe width alpha. You can write it as beta divided by capital D, or you can write it as lambda divided by small d. Do we understand this?
Yes, sir.
I'll give you a minute to note it down.
Okay, sir.
Well then, let us summarize what are the important points that we have seen for Young's double slit experiment. Now for Young's double slit experiment, what is the first condition? I will try to write all these points together so that you can find all things at one place. Number one, what is the first condition? The two sources must be coherent. Do we understand this?
Yes, sir.
That means the phase difference phi should be constant.
Constant.
They must have the same frequency. Coherent sources will always be coming from a single source, so they will always have same frequency. Do we understand this? Wave traveling in the same direction. Then we have amplitudes nearly equal. To get good interference, the amplitude should be equal. If the amplitudes are equal, then dark fringe will be completely dark and bright fringe will be completely bright. If amplitudes are not equal, the interference will not be good because dark fringe will not be completely dark Bright fringe would be bright, but dark fringe would not be completely dark. Do we understand this?
Yes, sir.
Well done. Then number 5, all the points written together. Part difference. Part difference is S2L. Do you remember this? S2L.
Yes, sir.
And that part difference S2L can be written as XD by capital D. X is the distance of the point from the central plane. D is the distance between the slits, and capital D is the distance between the slits and the screen. Number 5, for constructive interference. What is
Yes,
the
sir.
condition? Who will tell me? For constructive interference, this part difference delta X will be equal to n lambda. Do we understand this?
Yes, sir.
X d by d. So I'm trying to memorize everything together with you that I must remember about Young's double slit experiment. What is the next point that we should memorize? What will happen for destructive interference? Yes or no?
Yes, sir.
This part difference delta X will be 2n minus 1 times lambda by 2. And this is nothing but x d by capital D. Do we understand this?
Yes, sir.
Beta is the fringe width, which is the distance between two consecutive dark or two consecutive bright fringes. And you can easily remember that the formula is d lambda by small d. Yes or no?
Yes, sir.
Now you can write these important things about B, about beta. Beta is directly proportional to capital D. Do we understand this?
Yes, sir.
If the distance is more, you will have more fringe width, and therefore your interference will become very, very bad. You don't want that to happen. This beta is directly proportional to lambda. If you increase the value of lambda, beta will increase. Do we understand this?
Yes, sir.
This beta is inversely proportional to 1 by inversely proportional to d. That means if you decrease the slit distance, the fringe width will increase. Do we understand this?
Yes,
I'll give
sir.
you a minute to note all these points down, because there are certain points that I want you to remember, and we will discuss those points, 1 or 2 points only. And I will give those points, then we will solve some question to wind this one up. The next class, we will try to wind everything up. So 2 minutes to note everything down. This is YDSE in a single screen. I will send you the mind map, don't worry.
Okay, sir.
Then one more important thing that you must remember, sometimes a question is asked, if YDSE apparatus, or if YDSE is conducted not in air, if YDSE apparatus is dipped, or this YDSE experiment is conducted in another medium, it is not conducted in air, and this is a very important point, and this medium has a refractive index of mu, then what happens? Then what happens? Then what happens? Remember, remember, what are the things that happen when you conduct YDSE in a medium whose refractive index is mu? The speed of light in that medium will be c divided by mu. Yes or no? Where c is the speed of light in vacuum,
Yes, sir.
speed will decrease. You will remember this?
Yes, sir.
Now v is equal to f lambda. Frequency remains same, so the frequency in will remain same. So f will be equal to f dash. You will get confused between f dash and this, so I'll just remove this dash and I will use some other symbols. Frequency in the medium will be equal to frequency in the air. Do we understand this?
Yes, sir.
Frequency remains same, but the speed has changed. That means the lambda of the wavelength in medium becomes lambda in air divided by mu. Do we understand this?
Yes,
This
sir.
is the most important thing, that these three things, that lambda will change, speed will change. We have seen that in refraction. but the frequency will remain same. Please let me know that you have understood this. Therefore, you can see the fringe width beta. The new fringe width is beta m. Yes, beta?
Nothing, sir. Sorry.
The new fringe width is beta m. The new fringe width will become d lambda divided by mu d. Do we understand the difference between this fringe width and the original fringe width, beta? The original fringe width is in yellow. Do we see this original fringe width? It was d lambda by d. Yes or no?
Yes, sir.
And this new fringe width has become d lambda by mu d. Do we understand the difference? So
Yes,
I
sir.
can simply write the fringe width in the medium becomes equal to fringe width in air divided by mu. Will you remember this point?
Okay, sir.
This is a very important point that you should remember. If you dip the entire apparatus in a liquid of refractive index mu, the fringe width becomes beta by mu. It decreases. And why does it decrease? Because it is directly proportional to wavelength. The wavelength in the medium, as you can see here, the wavelength in the medium becomes lambda divided by mu. And that is the reason, bacha, the fringe width becomes beta divided by mu. I'll give you a minute to note this down.
Okay, sir.
Okay, then this is time
Am I
now.
audible?
Yes, beta, you're audible.
Okay, sir.
It's now time that we encounter some questions. This is the first question that we are going to encounter. Question number 8, this is from your sheet. And can you give me the answer for this one? The coherent source of light produces constructive interference when the phase difference is. We have got 4 options, A, B, C, D, and I am waiting for the right option from your end. Can I expect an answer here? Yes, beta? Sorry, your voice broke up.
Nothing, sir. Sorry.
Yes, beta?
Nothing, sir.
What is the answer for that one, beta? You did not get the answer for that one? For constructive interference, what should be the phase difference? No one has an answer?
2 pi.
2 pi is the answer. Oops, that is absolutely correct. 2 pi is the answer. Are we getting how questions are framed and how questions come? This is the next one. Again, question from your sheet. Can I have the answer for this one? In Young's double slit experiment, A, B, C, D. Question number 16. This is question number 16 from you, for you. Only interference occurs, only diffraction occurs, both interference and diffraction occurs, none of the above. Yes, I'm waiting for your answers. Which one? A, B, C, D, 1, 2, 3, 4.
C, sir.
Huh?
C.
B,
C, camel. C, camel.
C for camel. Both interference and diffraction occurs. When we produce those two coherent sources, it is produced by the phenomena of diffraction, and after that, interference happens. So it is an example of diffraction as well as interference. A very important point that you must remember. Will you remember it? I already told you in the class. Yes or no? No, yes.
Yes, sir.
Let us now move on to the next question. This is question number 9. Let me have the answers for this one. Phenomenon of interference is not observed by two sodium lamps of same power. It is because both waves have, remember, they are different sodium lamps, two different sodium lamps, and I wait for your answers. They will not have what,
A,
beta?
sir.
A, they will not have a constant phase difference. That is correct. You will not get interference. Are we getting? And
Yes,
we
sir.
understand, most of the question are theory based. There comes the next one for you. Coherent sources can be obtained. A, B, C, D.
Sir, C, camel.
C for camel, both by division of amplitude and wavefront. I have told you the example of division of wavefront, which is Young's double slit experiment. What is the example of division by amplitude? So you can write this interference in thin films. When you see interference in thin films, that is an example of division by amplitude. You write interference in thin films. Can you write it down?
Yes, sir.
Here comes the next one. And the next one is like this. Let me see. Can I get an answer for this one? In Young's double slit experiment, YDSE, width of the fringes. You have to increase the width of the fringes. Width of the fringes can be increased if we decrease A, B, C, D. And I'm waiting for your answers. I have to increase the width. What can I decrease? Separation of the slit width, distance between the slit and the screen, or wavelength. So this is
Sir,
small.
A.
Very good. This is small d. Width of the slit we have not mentioned. Let us call it as b. This is the distance between the slit and the screen. Capital D, and this is lambda. Remember, beta was lambda d by small d. Yes or no? We remember this, right?
Yes, sir.
If you remember this, then you have the answer. If you don't remember this, well, I can't help you there. That is the next question now. Question number 13 comes on your way. In Young's experiment, Young's double slit experiment, if the amplitude of the interfering waves are unequal, amplitudes are unequal, then what will happen? Contrast in the fringes decreases, contrast in the fringes increases. You have to apply common sense, and you should be able to give me the answer. And the answer is
Sir, A.
A. Contrast will decrease. Bright will be bright, but dark will not be very dark, because the amplitudes or intensities are not equal. Do we understand this?
Yes, sir.
Here comes the next one. Can I have the answer for this one? Young's experiment proves which of the following fact: A, B, C, D. Remember the name of this chapter and the reason why this chapter is known as what it is known as. What is the answer for this one? Question number 14 is what we are asking.
Sir, B, sir. Wave optics.
Yes, wave optics. Light is made up of waves. This phenomena cannot be explained by ray optics. Oh, this phenomena cannot be explained by particle nature, and that is why the name of this chapter is wave optics and not particle optics. Do we understand this?
Yes, sir.
Here comes the next one, bacha. Waiting for your answer. YDSE. I'm expecting one question from YDSE. Simple one. Which of the following is a true statement if in Young's experiment separation between the slits small d is increased?
B.
15b, fringe width decreases. It is inversely proportional to the distance. The fringe width increases, your fringes will disappear because dark and bright fringes will the fringe will disappear and you will not see much interference. Do we understand this?
Yes, sir.
See, the questions are pretty damn simple. I'll get one or more. Okay, these are based on this. Let me get with this and then probably we'll do it in the next class. In an interference pattern of two-way, fringe width is beta. If the frequency of the source is doubled, what will be the fringe width? Frequency is doubled. Frequency is doubled.
Sir, A.
Wow, how did you get it? Are you looking at the answers and telling me the answers?
No, sir.
Then how did you get it? Remember, V is equal to F lambda. Do we understand this? Yes or no?
Yes, sir.
Now, we are in the same medium, so V will remain same. Yes or no?
Yes, sir.
Now, frequency is doubled, so the wavelength should become half. Yes or no?
Yes, sir.
If the wavelength becomes half, then the fringe width becomes half. That was the way this question has to be answered. I hope you have answered it. Yes or no?
Yes, sir.
Well then, this brings us to an end of today's class. What we have done in today's class? Well, we have taken some giant steps for mankind. We have understood what is interference. We have understood what is coherent sources. We have understood that interference can only happen when there are coherent sources, wave moving in the same direction. For good interference, we need the amplitudes to be very similar so that dark fringes are dark, very dark, and bright fringes are very bright. We have also seen that the distance between two consecutive dark or two consecutive bright fringes is known as fringe width. Between one dark and one bright, it will be beta by 2. Beta by 2, no, beta is equal to d times capital D times lambda by d. If I dip it in some other medium where the refractive index is mu, lambda becomes lambda by mu, and therefore my fringe width decreases. We have seen some questions. We will continue and we will try to wind up interference in the next class and start with diffraction. We have also seen that YDSE includes diffraction because the way these two sources are created from a single source, that is diffraction. We will understand diffraction as well in the next class probably. Till then, have a good time and I hope to see you tomorrow. Be on time. I hope you will be on time in the next class.
Okay, sir.
Take
Okay,
care.
sir.
Have a
Bye,
nice day,
sir.
beta. Bye, beta.
Bye, sir. Take care.